San Diego. Tarun did his PhD in MIT in 2010, and his PhD advisor was Santil. And sorry, are we hearing some other?
Yeah, it seems like someone is not muted, maybe.
Please unmute. Please mute yourself if you. I'm hearing some sound. There's some background noise.
It seems fine now to me.
Yeah. So yeah, Tarun did his PhD in MIT in 2010, and after postdoc research in Berkeley and KITP, Tarun joined the faculty of UC San Diego in 2016. Sounds like there's some background noise, so I'm going to mute. I'm going to try to mute people, and if you need to speak, just unmute. And so yeah, so Tarun has done a lot of very deep works and very important works in many different topics, including topological states of matter and quantum entanglement in many-body systems in quantum field theory. Oh, I forgot to mention that he received prestigious awards such as Long Research Fellowship and the NSF Career Award. And today we are going to hear about a new topic from Tarun that's about simulatable models of nodal superconductivity and Kondo breakdown. So, Tarun, please.
Great. Thank you so much for this very kind invitation. And thank you for being here despite this being a really crazy week from just, I wouldn't mind at all if you are distracted by other things. Just don't get, yeah, it's like a bit like I was mentioning to Sri, that it's a bit like a character in dystopian movie reading a dystopian novel. That's the feeling maybe this week. But anyway, so let's start. So I'm really fortunate to have just absolutely fantastic collaborators. Xiaoyan is my postdoc, and Fakir Assad is my long-term collaborator from Germany, and Bimla, Johannes, and Toshihiro are from Fakir's group. At least formerly, Johannes was, and now he's working at Harrisburg. And Matthias Wojta, you all know. So, all right. So let's get started. So very broadly, I will be talking about. So I'm interested in some class of problems which typically, I mean, I don't know, questions about strongly correlated electrons, and the kind of perspective I want to take in this talk is how far can you push numerical studies of toy models which may have some interesting physics, which is generally, I mean, hard to obtain in in some solvable models or using some Monte Carlo generally. And can we construct toy models of things which are seen experimentally perhaps, or at least close to something like close to experiments, but without having fermion sign problem, which is one of the biggest obstacles in simulating fermionic systems. So okay, so you will see what these things mean. But the two topics I will discuss will be D-wave superconductivity and Kondo breakdown, heavy Fermi liquid phases. And I've been interested in those topics for quite some time. And so anyway, some models came along and we started thinking about them. So this is a motivation for the first part about the nodal superconductivity. So the very broad question we will be interested in is, are there models which can be solved without sign problem, which have Mott physics, nodal superconductor, and antiferromagnet together? These are the ingredients we need. Motivation is obvious. There are a lot of materials, as you know. I mean, ITC, and then heavy fermions, then this organic Mott materials. And generally the kind of obstacle is that when you have fermions at finite doping with repulsive interaction, you have fermion sign problem, which the talk is about, and I will discuss that more detail. So so what I'll be focused on in system at half filling, which still has nodal superconductivity. And for that motivation, at least for me, is this organic materials, which have on the verge of Mott transition from some unconventional superconductor. I hope you can see my cursor to some antiferromagnetic insulator. And there are a whole host of them. For example, I'm just showing some data on this organic materials. And they have nodal superconductivity. That I think is fairly clear by now. At least some of them do. For example, in NMR, you see T cube temperature dependence of 1 over T1, and at least several of them. So it's at least these things exist close to Mott transition. You have these nodal superconductors. It's not unusual. So so solving Hubbard model on some non-bipartite lattice, I'm not going to do that today. That's not, I don't know how to do it. So you'll be disappointed with if that's what you are hoping for. What I will be doing will be some toy models which have some of this at least same phase diagram, similar phase diagram, and try to at least see whether we can learn something from it. So if I want to summarize sign problem in just for fermions in just one sentence, this is how I will summarize this. It's the impossibility of doing simulations when you have Mott physics and Fermi surface. That's basically it, I think. So and the partition function, if you write down, I mean, and roughly speaking, when this happens, and I wouldn't prove anything, this is just an observation based on a lot of, just thinking about things and trying things and just have some feeling of the topic. When these conditions happen, and there's a Mottness and Fermi surface, partition function in any local basis cannot be written as sum of positive terms.
Sorry, I don't quite understand. If you have a half-filled model, there is also a Fermi surface before you consider interaction, and there is a repulsive interaction. I thought in that case you could have a Monte Carlo without sign problem.
You do not have Fermi surface. Whenever you're at half filling and you don't have sign problem, Fermi surface is nested, and you get rid of Fermi surface immediately. So you don't have both things at the same time. You don't have non-zero interactions and Fermi surface.
Are you going to define what you mean by Mottness?
Repulsive Hubbard interaction on site.
Oh.
Well, that sounds like that sounds like what if you have a different lattice structure where you have repulsive interaction, but you don't have this odd number of electrons per unit cell? Is that still Mottness?
Yeah, I mean, I'm not sure I followed. I'm just saying the Mottness are defined as a repulsive Hubbard U. That doesn't involve any bipartite structure. The fact that there's no sign problem, that requires bipartite structure. Sorry.
But, okay. It's a weird definition. I mean, if I had 1% of electrons on the lattice and there was a repulsive interaction, it would be of no importance whatsoever.
I mean, the physics may be singular at small doping, right? I mean, it's clearly there's at zero doping, you're allowed to have Mott insulator. At any non-zero doping, you don't. So in the thermodynamic limit, there's a big difference. Even
no, but you can still have an interaction. If Mottness just means there's an interaction, everything has an interaction.
Yeah. So I'm not following the question. Can you say what is the confusion? I mean, which part is not?
I just don't know what Mottness is.
Just repulsive on-site interactions.
Okay.
No, but that's the point. So
repulsive interactions, I understand.
yeah. Just repulsive interaction. It sounds like too general, right? If you can have a Fermi liquid with a little bit repulsive on-site interaction.
Let me be more precise. Mottness defines something so that let me stick at half filling. Okay, then it's maybe better. So let me define Mottness as some term which let you access a Mott insulator. It doesn't matter. I mean, I think let me just give me even one model which has repulsive on-site interactions and has Fermi surface and has no sign problem. It does not exist.
Two bands. All I need is 2 bands. I can do it. I could have an interacting model without a sign problem.
No, you do not have on-site repulsive interaction. That's okay. So a single band Hubbard model I'm talking about, single band, right? Okay. I mean, so I'm not sure. just restrict yourself to single band model. And if you can solve that, of course, that'll be great. I don't think anyone knows. So how to do
no, it's not about solving it. It's just about the statement that, mottness is a very ill-defined thing. I use it too, by the way, so that's fine.
Yeah,
But,
I think this slide is not the.
The statement just sounds a little bit overly restrictive, no?
Not to me. I mean,
anyway, maybe
it doesn't matter.
Let's go
What's the
on.
Hamiltonian?
That will come in the later part. This is not, I've not even started. So the Hamiltonian is later. So let me, so think about a system. Mott phase is an insulator, as I hope that we all agree. So if you want to access a Mott insulator while having Fermi surface in a single band model, that's impossible without having sign problems. So if you want localized electrons per site which are insulated, then you always are restricted to half filling and bipartite lattices. That's just a true statement. And so you have to choose between these two kind of sign problem-free simulations. If you want systems which have single band and are Mott insulator, then we don't know how to do it with Fermi surfaces. On the other hand, if you want Fermi surfaces, then you can have multi-band Hubbard models with interband repulsion, and even in those cases, if you look at your Hamiltonian, basically you have on-site attraction. For example, the simplest case which people have thought about is when you have consider two bands, and you have intra-band intra-band attraction and interband repulsion. So this is some work by, I mean, many people in the audience who have worked on this. Aries has worked on this, and so those are systems where you cannot have, I mean, on the on a given site, you still have an attractive attraction in the same band. So that's what I mean by that's yeah. So I wouldn't call that Mott physics, because you can put 2 electrons per site. So maybe this is another way to say it. You want a local moment. That's what I will call Mott physics, where you can have a spin half moment which can exist without being kind of bound to something else to get some local spin zero object. So that we don't know how to do it with Fermi surfaces. Is that somewhat clear? I mean, okay, maybe not. That's fine. We will see what the model is. So, so at least I would like to separate sign problem-free models in these two classes, where in one case you can have local repulsion, so you can have a well-defined local moment, so you can access, for example, I don't know, this near antiferromagnet. In this case, you can't, because I mean, essentially, when you do integration of any kind of electrons, you will generate attractive Hubbard U for the same band. And the issue with this is you will never be able to get if you work with this class of systems, you will never be able to get nodal superconductors, and that you can check in any of these models. The nodal superconductor is not possible. You can get a lot of other interesting things, and that's why I mean we do it. But here I'm interested in getting nodal superconductors. So anyway, yeah. So let me proceed. So so I'm interested in a model which has both a nodal superconductor and perhaps antiferromagnetism, and I want to study their competition. And neither of these phases require n-doping, and that's the main point. Generally, you will think of maybe within coming from high TC community that you have to do some kind of I don't know, doping to get interesting nodal superconductor, but you really don't need any doping, as you all know. So so can one find models which host both of these phases? And there's one very interesting proposal which came out when I was, I don't know, getting excited about calculus in my high school. So this was a Hubbard model, this standard Hubbard model with an extra term, with a kinetic energy square. So, and it has signatures of D wave superconductivity, but the signal is very small, as you can see here. So this is the D wave order parameter, and it's about 0.01. And this is 1 over L. So you have to argue at L goes to infinity, it remains non-zero. So it's not easy to argue that based on just this data. It looks perhaps promising. It's at least more prominent than S wave, but to really conclude that it's non-zero in thermodynamic limit is not going to be very easy unless one does more numerics, and one should do it. And that was kind of one of our motivation to find other models which probably have more definitive signatures. And so so this is the model we wrote down. So this is so there is a just the XY Hamilton. So the Hilbert space is electrons on sites and some rotor, a quantum rotor on link. And first write down the XY model for this quantum rotor. So yeah, this is a main. I mean, forget about everything. So this is a Hamiltonian. So if you get confused here, please ask me. So there's a quantum rotor model. So the nearest neighbor term for the quantum rotor, this is the nearest neighbor, this red bond. And then there's a coupling between this rotor and fermion bilinear, which has the same symmetry as a D wave order parameter. So, and H3 plus HU is of course just the Hubbard model at half filling. So so this is all the same symmetries as a standard Hubbard model. There is a charge conservation symmetry and a spin rotation symmetry. So this is it. So this is the model. So if there are any questions about the model, yeah, please do ask, because this is what we are working with.
So you have an infinite Hilbert space for the theta.
Yes, yes.
And you need to do some approximation later, I guess, for that?
Not really, because when you do, for example, Monte Carlo simulation, you directly work with some continuous variables. So you're sampling over some continuous space. It's not, I mean, it's not like, it's certainly harder than sampling over a discrete variable, but we do it all the time. For example, when you study Kosterlitz-Howlett transition, and even classical, you sampling over, just continuous space. So it's similar. So anyone who looks at this model, it must be obvious within a little bit of kind of thinking that it has D wave. So the taus are just numbers, -1 on the y bond, x +1 on the x bonds. So when J is large compared to K, theta condenses, and you just get BCS mean field theory. So clearly it has D wave order parameter, which is non-zero in some limit. The surprise is not that it has D wave order parameter. Surprise is it doesn't have sign problem. That's the main point. That's the main observation. At least we have been looking for such models for some time, and we did not think it will be easy or possible to find a nodal superconductor. I have not seen other models which I can argue doesn't have sign problem and show that it has D wave. So that was excitement, and that's why we worked on this. So you can, various limit, you can argue it has antiferromagnetic insulator and also some nodal D wave. So that I leave it as an exercise. So this is the mean field theory you can do. So one thing you quickly see, that there is an intermediate phase. And the intermediate phase, one way to think about that is that once you first go to the D wave phase, because
that there is more parameters, like you have 4 parameters.
Yeah, it doesn't. So we explored the space, and we chose. I mean, so there are no other, as far as we can tell, there are no other phases. So we took some slice which gave the representative phase diagram.
So this is like when J and T, how are the relation between J and T?
J, so that set J to some number, set J to 1 and T to 1 and V to 0.5.
So it doesn't matter T and J, which is larger.
I mean, it will move around the phase diagram, but the topology will remain same. So the main point is if you increase K over J or change G over T, you go from a nodal superconductor to antiferromagnetic insulator through an intervening phase. And when you think about this intervening phases in the nodal superconductor, the nodes are, because of the bipartite symmetry, because of the symmetry reasons, nodes are separated by pi. So when you condense Néel order parameter, you gap out these nodes. You still have some pi over 2 rotation symmetry in the D wave in this gap, and we use a notation from some work by Balance, Fisher, and Naik, which they call it DSCG. G means gapped, just the notation, but we know what it is. You just gap out the nodes, and so in this case there is a coexistence of antiferromagnet and superconductor at the same time. It's not like phase separation. Both order parameter has both things happening at the same time. So yeah. So that's.
Tarun, can I ask you a question?
Yeah.
So if I look at your model, HT and HU are fermions on a bipartite lattice, right?
Indeed.
Right?
Yeah.
So now if I integrate out the rotors, I just get additional long-range attractive interactions on top of that.
Attractive interaction, why?
Between pairs, because they couple to pairs.
Between pairs, yeah.
So in that sense, the original part with, V equals 0 had no sign problem. And with V not equal to 0, since you're only adding effective attractive interaction, it sort of makes sense that it should remain sign free, right? Or is that the wrong way of thinking?
I don't know. I mean, I can write down other things which have sign problem but have similar arguments. So it's not that straightforward.
Okay.
I mean, I can make it some triplet superconductor. I mean, there are ways to write down things which look argument goes through the same. I was thinking of the same argument, but it's not as straightforward, I think, because of those counter examples. So,
right.
Yeah. Anyway, yeah. So I don't want to say more. Yeah. So then you can study. Now you can do 1/L scaling, and it's very obvious that the D wave order parameter is non-zero in some regime. So this is different values of K, and this is the D wave order parameter as 1/L. So clearly there's a regime in which it is non-zero. And similarly, you can do scaling of antiferromagnetic order parameter is also non-zero in some regime. At least just here, the main message, don't worry about the numbers. Main point is you can basically show that it is non-zero and there is no ambiguity.
So just to confirm, so at finite temperature, the D wave order parameter will be like a KT, right?
Right.
So it's power law.
Yeah, but the antiferromagnet will not survive because it's O3.
Right.
Yeah.
But these results you show are at zero.
So we are mostly interested in finite zero temperature properties. So we scale beta with L.
Right.
But we also looked at some finite temperature properties and were able to detect a KT transition.
I see.
So that's all. I don't have the data here, but you can look in the paper. And then you can also look at AK omega. You can clearly see nodes in some regime where this is in the regime where D wave order parameters survive. I'm just showing the spectral function. And these are the various cuts as a function of K over J. So when K over J is small, that is J is large, you have nodal D wave. These are the nodes at the K points. And when K over J is large, you don't have any nodes. And in intermediate phase also, you don't have any nodes, as I already kind of argued based on mean field argument, and all that is correct. And everything seems to match. This is the gap for the electron. This is the spin gap. So you can also see the magnons in the antiferromagnetic phase. So everything is expected, what you would have expected based on, everything is what you will think based on low energy theory of these phases. So no surprises, but the point is you can get this physics without sign problem. And this is the phase diagram. So there are two quantum phase transitions, one between the D wave phase and the other from one from the D wave to this gapped gap superconductor plus antiferromagnet, other to the antiferromagnet. So in the first, so if you look at the second transition first, I mean, let's look at this transition. This is just 3D XY, obviously, because there's nothing else happening, because it's just antiferromagnet part is, I mean, spin rotation between is already broken. The charge is this U1, so you get a 3D XY transition. This one is more interesting because they are gapless fermions at this transition, in addition to, because we are going from a gapless quasiparticles to gapped quasiparticles, and you're also breaking spin rotation symmetry. So this is somewhat more interesting transition. So let's focus on that. And you can look at the anomalous dimensions, and you do some scaling collapse. Of course, these are small systems, so don't take these numbers beyond, like, I mean, 0.55 may become 0.6. So it's not like as accurate as some large scale like SSC simulation. This is small systems up till 20 sites, but at least we get some scaling collapse, and I will come to these numbers in a minute. So it turns out very similar phase diagram was obtained in some effective field theory description in some other context of pseudogap phase of high TC. And if we have time, we can discuss the motivation between this paper in relation to our paper. And they actually looked at this field theory for this transition already, and so we kind of borrowed some of it from their paper. And basically, you can write down the low energy theory for the critical point. It looks like there's some Dirac fermion. This is just the nodal quasiparticles coupled to some fluctuating nail, and this clearly breaks U1 symmetry, because on the both sides of the transition, global U1 is broken. So that's why there's a side dagger coupling, because you did some rotation. So anyway, so this is what you get. And then you start doing RG, and then we notice, okay, somehow RG looked identical to the conventional Gross-Neveu fixed point, or the Gross-Neveu-Heisenberg. For a while we were slightly, okay, at least for a day we were a bit confused and why that's happening. And then we noticed there's an interesting transformation you can do on this, which is this. You can do a rotation. It is not just usual particle rotation. It basically employs the fact that the free Dirac fermion has OH symmetry because of Majorana representation, and you map it to conventional Gross-Neveu Heisenberg fixed point. So, and then all the exponents based on large N, epsilon, and all the other numerics, and it matches with the exponents I earlier showed you. At least it's consistent with it. And there's a recent paper, another paper on where they looked at BCS mean field theory plus some Hubbard U. And you can argue based on what I've said so far that this is a correct way to think about this critical point also. It doesn't give you any spontaneous symmetry broken phase because you're doing BCS mean field, you've broken the U1 already. But it at least is a correct description of this critical point, because across this critical point, U1 was already broken spontaneously on both sides. So it doesn't matter. So the critical exponents you will get from this will be identical to what we are doing. But this may be slightly more useful because you can do larger system size because you're not putting this extra rotor. Anyway, so this is all the first part. So I hope I'm roughly halfway through. Yeah. So any questions here?
Question. Do you have any? So in your starting model, if you make a particle hole transformation on alternate sides of this bipartite lattice,
right.
What do you get?
I mean,
when U changes to minus U, what do you get for the other terms?
That's a good question. It's some kind of a like in the S-wave case, we know what happens, right? That you get the whatever Anderson pseudo spin becomes the usual spin and vice versa. Here, it's some funny kind of a charge order, I think. Yeah.
So it has some kind of SO4 symmetry at that point?
No. SO4 symmetries, I don't think there is SO4 symmetry here, not to my...
Well, you have 2 degrees of spin and 2 degrees of freedom in the,
No, but I don't think the symmetry is enlarged. That I think this
used to have SO5 when he used to talk about...
no, this model I don't think has that symmetry.
D wave, right?
Sometimes you can fine tune to SO4, but this extra term I doesn't have SO4 as far as I can tell.
well, it's certainly going to turn into some kind of an antiferromagnetic interaction if I make the particle hole.
Sure, but it's not invariant, right? That's my point. It will become something else, but it's not invariant under some SO4. There's a difference between going to, it will become something.
My question was, do you have any special symmetry at that point that you're looking at?
No, we don't have any addition. We have just the our symmetries are just U1 times SU2. Charge U1 times SU2 spin. There's no other symmetry. It's not SU2 times SU2. It is just
the minus sign freeness, though, that required you to have the kinetic energy just nearest neighbor, just bipartite.
Just bipartite.
Yeah. So there is a fine tuning there.
No.
That's fine, but
I'm just saying it doesn't have SO4 symmetry.
I understand.
Yeah, I wouldn't call that a fine. I don't call, if I can impose something by symmetry, I don't call it fine tuning.
But nearest neighbor is not imposed by symmetry.
No, there is a symmetry which is C up going to C dagger down on A sublattice, and C up going to minus C dagger down on B sublattice. That's a symmetry. It's the same symmetry which you use to get rid of sign problem. It's a real symmetry. So that symmetry makes sure you have only nearest neighbor, that you have only same sublattice hopping.
Yeah, no, I think this is the answer to Shree's question, because if it was really attractive interactions, you wouldn't need that.
Right. Okay, but I'm just saying, yeah, it's not fine tuning. It's a symmetry. I'm saying there exists a symmetry which prohibits same sublattice hopping. So, all right.
Actually, what I was saying is that his model involves two terms. One, which is a bipartite lattice, which has no sign problem, and another, which involves pairs interacting at arbitrary range, depending on what the J and K is doing. That also doesn't have a sign problem. So heuristically, nothing has a sign problem. That was all I was saying.
How do you see that the other thing doesn't have sign problem? Okay, you're taking in some large K limit, you integrate out and write it as a purely theory of rotors. That's what you meant. But
yes,
I mean, it has fermions, as we know. It has gap. I mean, eventually you have some nodal fermions, so you can't think of it as purely bosonic system, even though.
Okay.
Yeah, I don't know. If it were like an S-type superconductor, then I will probably agree. But if we're like, because nodes, it's kind of hard to say that. It's not a purely bosonic theory. Anyway, so if there are no other questions, let me keep moving to the next part. So that, I mean, I don't know. I'm talking about two different things which are unrelated, but I just want to give you a broad overview of the kind of things which one can do without sign problem, and it's looking like the range.
Sorry, I may be missing the point here. So when you compare this field theory with your simulation, is there some
I think this is sort of hidden here. I'm saying that after this transformation we did, we mapped it to something much more standard. I'm saying for this we know that critical exponent to fourth order in epsilon, and they match with these numbers to fairly good accuracy. That's what I see. Too fast, but yeah. So at least you have understanding of the phase diagram and the transitions in this model. And broadly speaking, I mean, I'm not trying to say this is model for anything real material directly, but at least from a topology of the phase diagram is very similar to what you find in these Mott insulators, which are these triangular lattice Mott insulators, where you have
But when you study finite temperature of this model, will you see that there is a competition between the two phases, which cause the TC to go down in the region? Or I'm just curious. In terms of the critical temperature.
As a function of what do you want to see critical temperature? As a function of
like this, the competition between the antiferromagnetic.
Sure. Yeah. I mean, it of course when it goes to zero at some point when you keep increasing Hubbard U. Yeah. I don't have it's somewhere in the paper, but yeah, it will, as antiferromagnetic set in, the TC keeps going down. Yeah. Okay, so let's keep moving. And so the second part of the talk is more about heavy Fermi liquids, and I've been, I don't know, thinking about for some time, and at least from the sign problem point of view, what can we learn about heavy Fermi liquid phase diagram using sign problem, free Monte Carlo? So so this is a famous Doniak's phase diagram, which has competition between RKKY at small jk to some heavy Fermi liquid at large jk, and the physics, of course, is in the antiferromagnetic regime, it's basically like some SDW metal. Essentially, you have antiferromagnetic instability of some Fermi surface, and you get some. This is at least a picture. You have AFM order, both for conduction electrons and for local moments. And at large JK, as you can see, I mean, it's just, if you take, for example, JK to be infinite, you form these tightly bound pairs, and the leftover fermions are moving around, and I don't know. So that's at least the naive, at least very simple-minded picture, which recovers a lot of physics. And what we want to understand is, are there things which do not have this simple kind of phase diagram? And there are a lot of materials now. Heavy Fermi liquids is a big field, and I don't know, phase diagrams can be arbitrarily complex, but at least if you try to look at the essence of what is new, are there things which are completely surprising? So there has been a number of works. So I don't want to, spend too much time on this, but I at least, because I'm not going to solve any of these materials directly, but I want to give at least a motivation. Is there any question? No, okay. So there's this one material which is cerium, palladium, aluminium, where the local moments live on a distorted Kagome lattice. And when people do neutron scattering, as well as NMR and various other studies which try to look at magnetic structure, but they find that 2/3 of the local moments order, and 1/3 seem to be not ordered. They can pick up which one is ordering, which is not, based on, I think, NMR. And so this is how the structure looks like. Some things order, some seem to be either Kondo screen, and perhaps in some other phase, maybe some spin liquid, who knows? But at least they don't have a movement. So, and there's a similar other material which has somewhat similar physics, this cerium, rhodium tin, and then there's this some completely other class of material. In this, again, in the cerium, palladium, aluminium, you can also kill this magnetic order completely by a magnetic field. And there have been claims that there is some intermediate phase which has perhaps some small Fermi surface fractionalized phase. So, okay, is it conclusive? No one knows, but at least there have been suggestions along those lines in this paper. And then there's this very old work on taking this ytterbium rhodium silicide, this famous material, and there have been claims that perhaps when you dope with germanium, there's some intermediate non-Fermi liquid phase which may have small Fermi surface again. And then there's also similar claims in iridium doped systems in the similar material, same material. There have been claims of some intermediate phase which is not a heavy Fermi liquid and not magnetically ordered either. Okay, these are all motivations, and we want to see whether we can perhaps cook up some models which have some physics resembling these things. So that at least there are two ways I will discuss, which take you beyond this Doniak's picture of having just two faces. One is add a geometric frustration axis, which is more like the cerium, palladium, aluminium. Other is dimensionality axis, reduce the dimensionality of local moments. For example, there's this very interesting work which came out in 2016, where they took cobalt atoms on copper. So it's very much like the work being done at Stanford, also by Professor Manoharan's group, which I will mention later. But this is like one-dimensional spin system on top of some metal. That's at least the rough picture. And then that also leads to interesting physics, which I will discuss soon. So let's first focus on the geometric frustration part. So the kind of models we want to study are this. So you have some, of course, they look super hard and complicated. There is some fermion term, which is repulsively interacting fermions. And you have geometrically frustrated spins, maybe some general graph, Jij, some general couplings. So it's have some geometric frustration and Kondo coupling. So this sounds really hard, right? Because it's Fermi surface, it's geometric frustration, both can cause sign problem. And just to remind you, I already mentioned Fermi surface sign problem without maybe giving you a lot of intuition, but for geometric frustration, maybe the intuition is a bit more straightforward. For example, if you have, this is called bosonic sign problem, essentially, which is bosons with kinetic energy, which has maybe a positive sign here. So consider, for example, triangular lattice hopping of bosons. So this has sign problem, but this doesn't because of this minus sign in front of hopping. And the way to think about the distinction between these two problems, one is positive hopping and the other is negative hopping. If we take in part integral, if you write on partition function, suppose you hop from 1 to 2, then you hop from 2 to 3 and hop back from 3 to 1 because you're doing trace e to minus beta h, you have to come back. You have product of 3 numbers, and they are allowed to be, because of this minus sign here, minus d beta, and h has a positive +1 here, you get -1 to the power cube, which is minus sign. So the partition function look like sum of terms which can be both positive and negative. So I only wrote down one term which is negative, but a positive term, of course, can also happen if you just pick one instead of d beta. So this is a sign problem for bosons. And the main idea which we are going to follow is that there is actually a relation between fermion sign problem, which I earlier mentioned, which is more based on auxiliary field Monte Carlo, where you integrate out fermions, and this bosonic sign problem. And the relation is the following. If you write down spins in terms of slave particles and impose the constraint exactly, I mean, you can find models where this constraint doesn't cause any sign problem, then the bosonic sign problem becomes a fermionic sign problem. The off-diagonal element being negative positive is related to fermion determinant being positive or negative. So that's an interesting relation. So it turns out if you really want to make progress on this Kondo system which are geometrically frustrated, you have to use this interesting kind of mapping. You have to work with spin-ons directly rather than spins. So I will come to specific models in a minute, but that's a broad idea to relate somehow fermion and bosonic sign problem. So which specific model should we study if you are interested in this materials? I already mentioned 2 class. So at least one, there have been already suggestion that if I take Ising frustrated Kondo lattices, so the frustration is more like in the diagonal component. For example, if I go back here, this is still geometrically frustrated because it's like ZZ, it's like a classical geometric frustration, if you like, ZZ interaction on a triangular lattice. So already there have been suggestions that this kind of frustration, when added to a Kondo lattice model, can give you physics which is very similar to this experimentally observed partially Kondo screen faces. So there's been a number of studies by Motomes and collaborator, and they were all like variational Monte Carlo or mean field theories. And we wanted, okay, we saw this way to make progress using sign problem free Monte Carlo. So we thought, okay, let's study such models. That's one thing I will talk about. And other possibilities, as I mentioned, non-Fermi liquids, perhaps which don't satisfy Luttinger theorem, can be also study them. So let's first do the first thing, the partially Kondo screen phases. So here's a model. I will try to be quick. So the model has conduction electrons on a honeycomb lattice. So if there is just hopping of them, you get Dirac fermions. Then the spins on each side, there's also a spin 1/2 spin, so the honeycomb lattice is 2 interpenetrating triangular lattice. So you can consider the AA coupling between those triangular lattice. So this is next nearest neighbor, like same sublattice on the honeycomb, ZZ interaction. So this is 2 triangular lattices. Right now, if there's only this term, they just decouple. But now everything is coupled together because of this Kondo interaction. So this is the Hamiltonian. I hope if the Hamiltonian is not clear, please do ask the question any time, please. I mean, it looks maybe complicated in the picture, but as I said, in words, it's fairly simple. There's honeycomb lattice for this, and 2 triangular lattice this, and local coupling. So so this doesn't have sign problem. Perhaps, at least to me, again, this was somewhat surprising. You can study these things. And you can't.
You don't have SU2 symmetry anymore.
You have only U1 symmetry. Yeah. Only the U1 symmetry, but that's enough to get you Kondo screening.
And there's no nearest neighbor exchange between the spins? We
can add that without sign problem with minus sign, but we didn't try it. It didn't seem to change what we wanted to do. We tried a little bit, if I remember correctly. I don't think it changed the features which we found. So if we don't have any frustration, if I turn off the frustration, JZ term, then we get just this very much like Doniak kind of phase diagram. You have anti-ferromagnetic insulator. Now you don't have heavy Fermi liquids. That's hard part that we don't know how to get even now because you're at half filling. But heavy Fermi liquid, as you know, becomes Kondo insulator when number of conduction electrons is number of fermions. But still there's a phase transition between these two regimes. All right, so when we do full phase diagram using quantum Monte Carlo, actually the most of the phase diagram completely changes. You get a completely different physics. So JZ is a frustration term. And so we get two new phases, and large part of phase diagram is the phase which is only because of frustration, which is actually a partially Kondo screen phase, very much like I earlier motivated from experiment. And I will explain that in the next figure what this phase is. But the overall phase diagram has two new phases, two different kind of partially Kondo screen phase, PKS. And one of them spins are ordered along the z-axis, so it doesn't break the global U1 symmetry because ordering along the z-axis. And I will explain that next slide. And this one is a bit more complicated version of this one, so I wouldn't get into it. You can look at the paper. But this z-PKS phase, the physics is basically you get some you break the lattice symmetry spontaneously, and you get an enlarged unit cell where different sites have different value of the magnetic moment. And you can guess perhaps because of the Ising frustration, on the A sublattice they add up to 0, and B sublattice they also add up to 0. The moments. And the interesting thing about this specific pattern of ordering, if you write down in low energy theory, what is the curse? You might think because spins are ordered, fermions will also order because of it looks like because S dot S coupling. You might think that just it's almost like applying a magnetic field. But if you write down the low energy theory, this is actually not a Dirac bilinear, which is it's not a Dirac mass. It's a fermion bilinear, which just shifts at just the level of mean field theory. It actually moves the nodes around of the Dirac fermion. Does not break any. Does not give you. So it's like a conserved quantity, like psi dagger rather than psi bar psi. So the mass that is, but there is still mass will be generated because of Kondo effect to the electrons. So it's a non-perturbative mass rather than a perturbative mass. That's an interesting thing in this phase, at least at the mean field level. So that's basically I want to say about this model. So at least you recover. So then we tried a couple other models, which is we never published it, but overall, whenever we have such Ising frustration, we always find such partially Kondo screen phases in Monte Carlo, which is also consistent with the kind of stuff we will see in experiments. The hard part is solving those precise microscopic Hamiltonian of experiment. These are just complicated systems. So with many bands, so we don't know how to do it. So at least these toy models give some kind of confidence that perhaps frustration, and it's not maybe surprising that happens because when you have some triangular lattice, if you do partially Kondo screening, you kind of relieve the frustration. That's roughly the idea. If you eat up, for example, one side of a triangular lattice, it looks like square lattice or something. So that's roughly the maybe reason this is happening. So the second thing I earlier said, can frustration lead to a non-Fermi liquid? So this is maybe more interesting. So this is this old scenario proposed by Sainthil Vojta and Sachdev that there's a possibility that spins can form a RBB state and fermions basically decouple from spins and form a small Fermi surface. So this is a genuine non-Fermi liquid because the Luttinger volume is not satisfied, unlike the heavy Fermi liquid. So the physics is basically, electrons are doing their RBB kind of motion. The local movements are doing their RBB motion, and electrons are just doing their own thing, the conduction electrons. So they kind of decouple. So can you realize such a state without sign problem? So the answer is yes. Again, you have to do maybe do a lot of work. It's heavy lifting, and a lot of credit just goes to Johannes Hoffman, who just it's a pretty hard numerics. So you consider Hamiltonian for the spins, which is basically the same form as the so-called balanced Fisher-Governing model, which we know has supports a Z2 spin liquid. And you have to do something funny with the Kondo coupling to get rid of sign problem. Put some sites have ferromagnetic, some anti-ferromagnetic. That's the price you have to pay. I think there's a way around that, but we didn't. I haven't studied this other models. But anyway, this is the kind of Kondo coupling you write down. So the electrons live on the honeycomb lattice, which is by this. So the blue and the red ones form a honeycomb lattice, and the spins live on a Kagome lattice. So model is a bit involved, so I don't want to maybe spend too much time. But roughly, because of geometric frustration of the Kagome lattice, you get this. If there's no other coupling, you get a Z2 spin liquid. And again, the way to solve this is without sign problem. So the naive case, you might think you do SSC on spins, and so I want to emphasize this. So there's a lot of recent work follows in the following, like this work for example, on nematics, right? When you study nematic instability of Fermi liquid, the way to do that is to couple, for example, some term which is diagonal in your measurement basis and to fermions, and do basically stochastic series expansion on those bosonic variables, and do determinantal Monte Carlo on the fermions. And this is in fact the same thing with our D-wave model. You do think of theta as you work in the theta basis, so it looks like SSC for theta is bosonic variables and determinantal Monte Carlo for fermions. And the point I want to make is that's not the case here. Here you cannot do that because the coupling is both diagonal coupling of fermion and off diagonal coupling of fermion because of this Kondo interaction. This was the case even in this previous model I showed you of this partially Kondo screen. So that's the reason you have to work with some spin-on representation and impose the F tag or F constraint exactly using Hubbard U, which you can take to be infinite because of there's no sign problem in this case. So that's the important distinction from technical point of view between these class of models and those other ones. So and schematically you get this phase, you get a fractionalized Fermi liquid, and you get a magnetic insulator. You don't because of this funny coupling, you don't really get a conventional heavy Fermi liquid. You get a magnetic insulator. Anyway, so but the main point is this fractionalized Fermi liquid has a small Fermi surface. If you just write on a symmetric state, which is a heavy Fermi liquid, doesn't break any symmetry, it will have a large Fermi surface with the actual Fermi surface. In our case, this phase has a small Fermi surface of Fermi volume 0. It's just a Dirac fermion, which is inconsistent with Luttinger theorem. So, yeah. Mm-hmm.
Sorry, but it's really it's a semi-metal star.
Yeah, it's a semi-metal.
It's not
star.
Really a Fermi liquid. It's
no, I just meant in a more general sense. Yeah,
yeah.
Semi-metal star. Yeah.
Yeah.
So and you can detect a transition. One kind of interesting.
Sorry, what is the star in semi-metal star?
It's coexisting with a spin liquid with a topological order.
Oh, I see.
Yeah.
Okay.
So, how much time? Okay, we still have time. I hope 5 minutes. So
Tarun, related to that point,
yeah.
The Kondo temperature is also not going to be the same, e to the 1 over j, right? Because there's no density of states.
That is true. That is true. Yeah.
Okay.
So let me. I think I don't have much time, so let me move ahead. But this is the physics you get, and you can study the critical point also, and you can argue based on RG that even at a critical point, Kondo coupling is ineffective precisely because of fractionalization. So the Kondo coupling RG at a critical point involves the critical exponent eta of the spins, and eta is bigger than 1 in fact, because of the fact this is a fractionalized space, and Kondo coupling is irrelevant even at the critical point. So there's an interesting consequence even for the critical point. Anyway, so the next part I want to mention is this dimensionality effect of going beyond Downing phase diagram. And again, so this is the kind of experiment, cobalt atoms on some copper metal, and this is very similar to this recent work done at Stanford also. So and there's a modeling of this experiment, fairly detailed modeling of this experiment. All the features were reproduced by a Kondo lattice model, where conduction electrons are the lower copper ones, spins are spin 1/2 of. So again, you might say cobalt is spin 3/2, but because of the anisotropy, it becomes actually effective 1/2 once you take into account the Jan-Tyler kind of effect. So then the coupling is just Kondo coupling, and we don't add magnetic field in our paper, but this is the kind of model we want to study. And then there's another experiment on this ytterbium ytterbium platinum material, which has this. It's a 3-dimensional system which has metallic response, I mean, for everything, but it still shows 1D spin-ons. And you can again effectively basically it's spin 1/2 chains embedded in a 3-dimensional metal. So you might wonder why is there no, I mean, what's going on? Why are there spin-ons? Why are they not getting Kondo screened? So this is the kind of question we were interested in. So we studied one toy model. Now we are doing more other things, but let me mention one thing we did. So we studied consider Dirac fermions, so of conduction electrons, Kondo coupled with Heisenberg chain. And this was already interesting. It has not been studied to our knowledge. So this was kind of, because there was an interesting feature here, which I'm going to mention next. And this doesn't have sign problem again. That's interesting. And the low energy theory becomes basically Dirac fermion Kondo coupled with some Néel order parameter, where Néel order parameter is coming from this 1D Heisenberg chain. So this is some Wisdom-Witten theory of 1D Heisenberg chain. So this is a bit like an intermediate thing between a single impurity Kondo and the usual Kondo lattice. Analog of Kondo impurity here is a 1D CFT. So your coupling is there's a dimensional mismatch, but not of D, but if you like D-1 between the conduction electron and the local moment. So, and you can, based on RG, you can argue that this decoupled point where JK is 0 is actually stable fixed point. So that's the main point. So you can have well-defined spin-ons because of just the way scaling dimensions work out. And then you can study this interesting Kondo breakdown critical point because of the dimensional mismatch and because it's a semi-metal. You can study this in fair detail using RG, and you find some interesting critical exponents for this intermediate fixed point. In fact, the epsilon which you perturb in is something like D-3/2. So things become marginal in 3/2 spatial dimension for the fermions. So epsilon equal to 1/2 is what you are, is your physical case. So it's kind of nice to have one example where your epsilon is not 1, but 1/2, less than 1. So that was nice. And you can study a lot of property of this critical point, and you can match, some things you can at least see numerically also. Not so much about critical point, but the phases you can see very clearly. And that's in fact, and sometimes the point that you can study this thing numerically. So you find at small value at JK, you find up till some critical point, up till 2, you find well-defined spin-ons, and after that it behaves like heavy Fermi liquid.
So Tarun, in your model, with epsilon changing, the CFT still remains strictly one-dimensional, right? Is that right? Or?
CFT, no, I wouldn't say that. No, because because it's coupled to you're coupling a 2-dimensional CFT with a 1-dimensional CFT. So the critical point has both things together. Like the Hilbert space has both a 2D CFT and a 1. So it's hard to, I don't know how to even say this is a,
No, I just meant that the dimension that's changing is that of the 2D thing, not of the 1D thing.
Exactly. Yeah, exactly. Yeah. Okay. Yeah.
Okay.
Yeah, right. Because I want to, that's why it's an interesting kind of RG calculation. I'm not doing perturbative RG around some free fixed point. It's not a Gaussian fixed point I'm perturbing. I'm perturbing a interacting fixed point. So that's why you have to do the usual conformal perturbation theory using OPE rather than some standard epsilon expansion. So anyway, and you can see spin-ons up to some critical point, and then they go away. And interesting, I don't know, do I have 1 more minute or should I stop? Maybe.
Yeah, we had a lot of discussions in the middle, so
okay.
The other 2 more minutes.
Okay, it'll take just 2 more minutes. One thing you can see in the co-tunneling, so you can look at zero bias co-tunneling between you have some STM tip and you're trying to tunnel into the metal going through the spin 1/2 localized moment, and it clearly shows this Kondo breakdown phase. So this, I think, is an interesting thing to think about experimentally. This could be one way to detect some of these things even in heavy Fermi liquids. Up to some point, it's basically zero. And so the very last thing I want to mention is an idea which we've been playing around with is how to detect. So all the stuff I mentioned in my last part of the talk is about a gapless degree of freedom, like some Fermi surface or semi-metal coexisting with some spin-ons. So that's interesting. So these are kind of, if you like, semi-topological. They're topological degrees of freedom, and they are this gapless degree of freedom coexisting. So how to detect the topological order, given the background of this gapless charges? So that this is one when we think about one proposal. So take your fractionalized Fermi liquid and do a projective measurement of electrons. So measure all of them together, like exactly what the measurement does. Find their spin charge. Everything is just becomes a C number once you measure electrons. So electrons are gone after projective measurement, and look at the new wave function that you obtain. The claim is that wave function will be identical to that of a RBB-Z2 spin liquid at low energies. So this way, you're not integrating out electrons. If you integrate out gapless stuff, you generate all kind of non-local stuff. You don't want to do that. You want to project out. And it's very much in the similar spirit as all this recent work on hybrid circuit, but also related to its quantum disentangled liquid, which we're working long over with Matthew Fisher, and that actually the origin of the idea. And the claim is initially you have this L log L entanglement from Fermi surface because of the small Fermi surface, and that basically hides all the topological order because it's somewhere. It's very hard to define topological order when you have L log L term, because this is not a UV term. It's all IR. So how do you cancel out L log L? There is no. If you do ABC subtraction of Kitaev-Prescott-like scheme, it will not cancel out this term ever because it's IR degree of freedom. But if you do projection, you completely get rid of L log L, and you're left with area law, and then you can study the useful topological order using conventional techniques. So to kind of get some understanding of this method, we studied one simple case of a gapless topological SPT. A gapless SPT phase. So it's a spin 1 model of bosons. Bosons carry spin 1. This was originally introduced in this paper by Hongchen and collaborators. But there are 2 phases. One phase, so there's a charge and spin because it's a spin 1 boson. In one phase, there's a gapless SPT phase where there's a charged Luttinger liquid and Haldane spin 1 basically coexisting. So that they decouple at low energies, the spin and charge. Charge enters the Luttinger liquid, and the spin forms a Haldane phase. And in the other phase, the charge forms the Luttinger liquid, and spins are in a trivial phase. So they're not they don't form a Haldane it's not AKLT, but a trivial SPT phase. And there's a phase transition between them. So the central charge is 0. Central charge is 1 here, central charge is 1 here, and central charge is 2 at the critical point. So we follow over this intuition about projecting out degrees of freedom. So we measure the charge, and so look at the difference between the without measuring and with measuring. Projection is just a measurement. If you don't do projection, you look at the entanglement spectrum. It's basically very hard to see any kind of edge states. At least it's.
Sorry, what's the x-axis?
X-axis is the eigenvalue index of the entanglement spectrum.
Oh.
And this is look at the reduced density matrix. So first the measurement of charges, then leftover wave function is only of spin. In that resulting wave function, separate into region A and A bar, and look at a reduced density matrix of region A, and look at the entanglement spectrum. And the point is, after this, if you don't do projection, you're completely polluted by this gapless degrees of freedom, the CFT part. But if you do the projection, you clearly see the edge states. And these are different values of parameters, but they are all in the same regime, which is the large J regime over D. So this is, and so I don't know, I didn't demonstrate that extracting topological order to you because it's a much harder calculation. It requires variational Monte Carlo of a fairly complicated kind, but at least the idea seems to be working, and more, I don't know, it'll be good to just do more along this directions of detecting topological order in the presence of gapless degree of freedom using this. But yeah, so that's about it. Yeah, so these are the summary and question. I will highlight maybe a couple of things. One is this: if I take the original superconducting model, nodal D wave, it's an obvious thing to try with studied with DMRG at small doping, because you already got a superconductor. If you want to maybe access nearby physics of I don't know, charge fluctuations, maybe it's a good starting point for DMRG, because generally hardness of DMRG depends on how much you dope away from half filling. Half filling doesn't have sign problem, so but it also has no. So then I would think that even at small doping, unlike the case of the Hubbard model, we have to go to some finite doping to access perhaps, or we don't know whether there's superconductivity there, but at least seemingly have to larger doping.
Sorry, I'm confused. What does the minus sign problem have to do with DMRG?
No. I'm saying that if you have a sign problem free model, and then you dope it to get a model which does have a sign problem, I would think the hardness of DMRG depends on how much you have doped.
The hardness of DMRG?
Really?
Yeah.
Why does it depend on how much you've doped?
I don't know, because that's amount of, I mean, I've been told, I don't know, because if you have few holes, it's easy to do DMRG, for example, in Hubbard model. If you put finite density of hole, let's say 0.
Well, the Hilbert space effectively is bigger, but other than that.
Okay, this is just, I'm just looking at some of the papers people have written, and that's what they say. You can, I'm not an expert, but.
I mean, DMRG really depends on how many, how big your central charge is or how long your correlation lengths are.
But if I look at all the recent work on when people were trying to search for D wave in the Hubbard model, my understanding is the bond dimension becomes larger and larger when you go to larger doping. Isn't that correct?
I don't think so.
Okay.
I mean, you just don't expect to find superconductivity at larger doping.
But effectively, the Hilbert space dimension is certainly going up because the possible number of states is going up.
Right.
No, it isn't. Not for the Hubbard model.
Well, there's charge conservation.
But half filling has as big of Hilbert space as in fact, I think the Hilbert space doesn't change much.
It's maximal.
There's basically 4 states per site.
Yeah. Sorry. Okay, I thought it was TJ.
With the TJ model, you would be right.
Right. Anyway, it may be interesting to study this model with doping if you are anyway, because it has a at least this model has a D wave superconductor. So
yeah,
that's all.
Okay. Yeah, I think we should thank Tarun before we take all the questions. Thanks very much. Yeah, so let's have some more questions.
I have more questions, but other people should ask first.
Can I ask a question? So you studied lots of models with Ising anisotropy. Could you do something with just XY spins?
Depends on what you want to. I mean, you clearly can't add frustration, which gives sign problem with XY spin. I mean, if, for example, as I don't know, so which I mean, I'm not following that question. I mean, are you asking? I mean, can be more specific? I mean, here's XY. This is XY.
I was actually more thinking about the other model with the frustration, but okay, but either one.
Yeah, but you can always add a minus J per S plus S minus. That doesn't change the physics much. We want to give maximal chance of frustration. So if we add a term which favors antiferromagnetism, magnetism, we don't want to we're interested in phases which are not this conventional phases. to
No,
maximize.
but what I was asking is if you replace this JZ with like a J in the XY plane, and I would have, you know, S dot S in plane.
No, that's what I'm saying. I meant J. That's what I meant. J perp. S plus S minus is SX plus SY. So I'm saying if I add that term on a triangular lattice, there's a sign problem if the J perp is positive.
Okay.
So if J perp is negative, the XY term.
Sure. Okay.
Then I'm saying then you're favoring antiferromagnetism, and we are trying to maximize effect of frustration. So that's one reason. But if you add it a little bit, it doesn't change the phase diagram much. But obviously, I cannot solve the Heisenberg model on a triangular lattice. That just, is, I don't know. No one knows how to do it, so I'm not going to solve it here. I mean, with antiferromagnetic XY term, yeah. Yeah. Is that answer? Does it answer the question?
Yeah, it does.
I have a naive question. So
yeah.
In the D-wave superconductor model, when you have a half filling, I realize it's maybe just because I didn't think about this problem much. I mean, what is the superfluid density? I mean, usually in a doped multi-insulator, we think it's just the doped part, which is superconducting. So it will be whole lag or electron lag, but
right.
Here it's like half filled.
It's basically like I think it's proportional to the average value of. I mean, I think it's proportional to the superconducting gap, if I remember correctly.
Oh.
No.
It's usually proportional to the Drude weight, but
I think it's.
I mean, I assume there's a way to tell whether it's electrons forming cool pairs or holes forming cool pairs, or
no. Superfluid density doesn't have a sign.
Right.
I mean, you're at half filling, so I'm not sure there is such a thing as.
Okay, so there, I guess there's response. No. Yeah.
Or the thermal Hall effect or something. It's probably zero by particle hole symmetry, but the superfluid density is an interesting question.
We calculated it, the rho S, we calculated using just the usual twist method. And I mean, the trend is such that it is large where the gap is large, and where gap is small, it is smaller. So yeah, I don't know anything more to say right now.
I mean, in a conventional Fermi liquid, it's independent of the gap. So a usual superconductor, the superfluid density is independent of the gap.
Yeah, but here he has got the bosons which contribute to it, right?
I know.
So that's where it comes from.
Oh yeah, that's right.
Yeah, I don't know, like some analytical expression, but that's the trend.
Steve,
yeah. So let's see. So first, the last thing. Can I think about this in the following way? So if I have a Z2 spin liquid and I turn on some disorder, I still have a Z2 spin liquid. I don't harm the topological order. So suppose I think about your Fermi liquid star,
right?
And I turn on disorder. And I turn on it up strong enough to localize the electrons, which in 2 dimensions is easy,
right?
But weakly enough that I don't destroy the topological order. And then I measure the entanglement entropy the usual way.
I think so. I mean, that is totally fine. I mean, in fact, I would say that for like impurities are doing the measurement.
Right.
Yeah.
Okay, good.
Yeah.
I just wanted to make sure I understood.
Right.
So there's something I haven't understood. I mean, you're right that finding a nodal superconductor, for instance, has been really hard in sign-free Monte Carlo calculations.
Right.
I mean, not hard. This is a first. So that's exciting, but I haven't understood what it, so I understand that your model is sign-free. That's just a mathematical statement.
Right.
And I understand that it's got a nodal superconductor. That's a result of your Monte Carlo calculation. But I haven't understood what it is about this model that made it give us this nodal superconductor.
I mean, I don't have a kind of some deep answer. It's just I think I just find original. Let me put it this way. I mean, there's some kind of I would say sign problem compatibility. Two things go together, and that's what I was trying to get to earlier, which I think no one liked. I was trying to emphasize this point, is that there's some kind of a tension between at least in a single band model of trying to have a regime where you have a well-defined Fermi surface, and also a regime where you have well-defined local movements. And I think that's and I mean, that's the same.
No, but that we do and do it within a sign-free model.
Yeah, of course. Yeah, that's what I question.
Yeah, I don't know.
I think that's the hard part.
I mean, how do we know that the existence of the node has to do with the existence of local moments?
No, that's what I'm trying to say. I'm saying from the effective, if I think from a low energy theory point of view, within some, I don't know, this old, I don't know, flux or any of these kind of way of thinking, if you have a single band model and if you have got antiferromagnetism, then it can give you superconductivity in the D wave channel in a single band model, right? So I'm saying there's sort of a sign problem compatibility of certain things. So the nodal superconductor is fine to coexist with antiferromagnetism, and to get antiferromagnetism of this kind, I need sort of this anti-particle hole time reversal rather than the usual particle hole. So, and this is how we came to the model to begin with, but there's sort of a compatibility.
I have to think about it. I still don't understand, but thank you. Anyway, the results are very exciting.
Tarun, I think the answer to Steve's question is that you have two sectors. You have some rotors and you have some fermions, both of which are sign problem free, but the coupling between them involves products of two terms, one which is fermionic and one which is bosonic, each of which are not sign free, right? There's these taus you had.
No, it is sign free. That's the point. The point
Well,
is this term.
Because it's the product of the two, but
No, irrespective of tau I, you can set to anything, and e to the power I theta is just in Monte Carlo. These things are fixed numbers, so any phase here is fine. The point is this term is just invariant under anti-particle hole symmetry. Yeah. For example, just to give a bit more intuition, suppose you say, can I get, for example, some coexisting S-wave superconductor in this model?
Mm-hmm.
You can't, because that will start giving you Fermi surfaces. You can combine S-wave with D-wave, and you will see that there's parts of Fermi surface which remain gapless.
So to confirm,
no, that'll just move the node.
No, okay. I mean, I don't know what exactly but there are ways to do it with S-wave, which this is some work by, okay, this guy in Minnesota. Sorry, what's his name? But anyway, you can do mean field. You can get,
if you get D plus IS.
Yeah.
That breaks time reversal symmetry, and that gives you Fermi surfaces. But just D plus S just moves the node.
I'm thinking D plus IS. Yeah.
Yeah, D plus IS, but that breaks an additional symmetry. That breaks time reversal symmetry.
Mm-hmm.
But so are you saying if you have a model of only the fermions with this pairing term, let's say if the theta is a fixed value, so just this term with a fixed value theta equals 0 everywhere, is that also sign problem free?
Yes. Otherwise, it doesn't work. The way Monte Carlo works is for each fixed configuration of this fields, you have to have a positive determinant. So but I'm trying to say there's no way to, I mean, you do anything here which tries to give you a Fermi surface, you'll get sign problem.
And
So
Tarun, are the nodes always at pi over 2?
Exactly, that's fixed pi over 2, pi over 2. That's fixed by the particle symmetry. They cannot, and it's all related to the fact there is no sign problem. And I mean, I don't know. I actually stand by this statement. I mean, I wrote this based on something.
No, I don't find the definition of mottness. There's no real definition of mottness. That's why it's in
quotes, right? But I'm saying that's why it's written in quotes. But my point is that once you have write down a model which has which tries to give you local moment and also try to and have Fermi surface, then you get sign problem. So that's why when you have like Dirac sign model, you don't have sign problem because you have well-defined, I mean, Dirac, like this cross neighbor transition, you have well-defined local moments, but you don't have anywhere Fermi surface. But if I look at your model, for example, of the nematic case, you will never be able to add and if you do, for example, if you integrate out fermions in your model, you will always generate attractive Hubbard. You can just check it. I mean, I'm sure you have checked it. So that's why there's always, if you, the kind of superconductivity you will get in those models which have Fermi surfaces will be always S wave.
Yeah, I agree.
But I'm saying that's the tension I'm trying to describe in this previous statement. I'm saying,
I mean, the model of the antiferromagnet, they get something that's formally a D wave, but it's a S wave in disguise.
It is S wave. That's my point. That model which you're
no, it's not S wave. It's D wave in terms of point group symmetry, but it's S wave in disguise.
It's S wave in this sense. That's why I say that it's not. It doesn't have a Mott physics because it has minus on the same side. You have up and down fermions from the same band, but on different bands repel each other, but same band are sitting on the same side, and that's what I mean by Mottness. And that model has absence of Mottness in that sense. And obviously, I'm not making it precise, but I'm saying if you look, it's based on collecting kind of intuition from 50 different models. This statement, so it's not like it has some truth, but I don't know how to make it more precise. But yeah, I mean, as you have already seen, this work by Ares recently came out. I have not cited here. Maybe there's this. One of the reasons it's hard to access physics of non-Fermi liquid, for example, of the kind like in this RPA, whatever, this spin-on Fermi surface or the nematic, is precisely because at low temperatures you start getting S-wave superconductivity. It hides all the interesting non-Fermi liquid physics. And anyway, so it's kind of all related to the fact that you can't localize a moment and have Fermi surface at the same time.
Before continuing the discussion, I would suggest we follow the tradition of the in-person seminars and thanks Tarun again, and then people who want to view will view, and we can just continue. I don't have any time restriction until unless like Tarun needs to.
Sure. I have a meeting at 5:45. I have more than an hour, so.
Okay. Thanks very much.
Yeah, thank you for all the questions.
Yeah,
thank you.
So we can continue. Yeah.
Yeah, actually, I have to do something.
Thanks.
So.
Okay.
Sure. Thank you.
Yeah, I actually have another question. I don't know, people are probably leaving. So this measurement idea is very interesting. Yeah, it's you project measurement and then you
right.
Then you. So my worry is it's I mean, the topological order is robust against local perturbation, but this is not a local perturbation. So I don't know how, yeah, so is this robust? Like if I take a general system, how do I know like which kind of measurements can kill the topological order, which kind of
it's a very good question. But I think the idea here is that precisely because at low energies, the degrees of the things you're measuring at low energy decouple. That's the whole point of this fractionalized Fermi liquid. At low energy, there's a decoupling in the effective field theory between these gapless degrees of freedom and the topological order. And what you're measuring is precisely the things which kind of don't couple.
Yeah, but they are coupled, they are entangled. I mean, you have a function of these.
Yeah. You have short range entanglement. So you can ask if I So you can try to justify it within a part integral that you can try to do. So write down the low energy theory with the irrelevant terms, include everything, and try to look at, if I do this projection, I get some new wave function. What is the effective field theory for that? And at least in some examples, you can argue that at some fixed points, you can argue that it doesn't change the physics. It's not a proof or anything, and I agree that's a valid concern, but at least in some cases you can argue it doesn't cause any issue. And it's,
yeah, I think it's a classification question. It's like maybe a priori you need to already define two kinds of degree of freedom in the macroscopic level.
Right.
And
right.
then you maybe topological order of one system A is robust against measuring B. But yeah, but like if you have you can imagine a system where you just have one kind of electrons, but it forms this kind of gapless degree of freedom together with the topological order. Then it's not always how you separate them and how to do this kind of measurement. I mean, like the gapless thing could be macroscopically from the same electron. I mean,
right.
Yeah, but I think this is it's a interesting. It seems like a totally new.
Actually, I have one more thing to say here. Yeah. So there's an inequality we found. This is in this paper with John and Daniel Benzion. Between this projective object, like you do the projection and look at the entanglement after that.
Yeah.
And some kind of conditional entropy, which sort of what we are after here. Sort of like we are saying that you're conditioning on that. So there's using some, I don't know, ways, using strong sorority and so on, you can prove that. And that was somewhat interesting. And then you can check that inequality, how close to it's saturated. And in some of the example we were interested in, not this one, and some of the other example, it's fairly close to saturated. But at least there's a relation between this quantity and some more usual, maybe objects which do not involve projective measurements, but are more like conditional mutual information.
It's like conditional mutual information.
Yeah, we looked at two different things: conditional mutual information and also some conditional entropy like SAC minus SC. So for both of them, there is some inequality between this kind of object and that object.
Yeah, maybe you can tell me more tomorrow. I think this generally, it seems like a very interesting new way to classify phases also.
Yeah.
I don't know what's the most general way to do that if you only have one kind of macroscopic degree of freedom. But
right, that's a very interesting question. So I don't have a good answer, because there also exists this this fractionalized semi-liquid where there is only one kind of electron. There is no like two different. It's not like Kondo lattice model, and this is this recent work by Subir, for example, on Ancilla qubit approach, and they just physically there's one kind of electron. So what are you going to measure? How do you kind of define two things? There's something there, but I haven't really understood it. It's
okay. Anybody else have questions? Okay, so I will see you tomorrow then.
Yeah.
Thank you very much.
Yeah. Thank you for this. Yeah.
That's really helpful. Yeah.
Yeah.
Bye.
Bye.